The next problem that we are going to tackle is the following. If you look at the diagram, it says the square ABCD has sides of length 6 units. So the square that you see there, all the sides have length 6 units. So that is what it is saying. Then it also goes on to say that M is the midpoint of AB. Okay, so this square here, all the sides have got length 6. So you can see I've got, this is 6, for instance. And M is the midpoint. That means it's right in the middle of AB. So in other words, each part of this is 3. Right? Okay, and then they say P is a variable point on BC. That means that P can be anywhere on this line here, BC. And the question is, what is the smallest? Find the smallest value of dP plus PM. So let's just trace dP. dP is that one plus PM. So when you choose the point P here, then dP has got a certain length and PM has got a certain length. And you add those two, you get a certain number. Now, it's quite conceivable that if you choose a point P here, for instance, somewhere there, then dP is that, and PM is that. So dP plus PM will be different from dP plus PM here. So the question is, what is the smallest possible value of this? So if you take all these points P, which point will give you the smallest possible answer to the sum dP plus PM? Well, that is a it's quite a challenging problem. How should we do this? Unfortunately, there is a strategy when it comes to problems of this type. Right? So what we say is we'll try to make dP and PM, to try to make dPM a straight line, because then the straight line is the shortest possible point. But now, no matter, this dPM can never be a straight line, right? So what do we mean by saying that the straight line is the shortest distance between two points? So a little bit of thought will tell you that what we have to do is you can take this M and push it on the other side. Right? If you take M and reflect it, in other words, you imagine that this thing here is a mirror and the M is looking at itself in the mirror. You'll see just now why we are doing all this. Then you will get a new point across the mirror, which we could call M prime. So we'll call this point M prime. Now, you have to make these two equal, because we are saying it's a reflection. Right? And then you have 90 degrees here. And the nice thing about a setup like this, where you got a blind segment and you got the midpoint and you got a perpendicular line, I mentioned this in a perpendicular line, then any point on this perpendicular line is equidistant from the two endpoints. Let me explain what I'm saying. So now if I take M prime to be that, then you will see that the line P M prime. If I join these, what I get now is two triangles. And these two triangles are congruent because you got angle here. These are equal. This is a common side, right? They're congruent. So in particular, your PM, which is part of the sum, dP plus PM, this PM is the same as that line there. Because these two triangles are congruent. So when you're looking at dP plus PM, it's the same as dP plus PM prime. Now understand, M prime is created from M. All you do is you go up to B and you go the same length to the other side, right? So M prime is created from. So once you got this, now the sum that you're looking for is dP plus PM. Now P is a variable point. So when P is here, for example, then you will have the dP plus PM will be like that. Now, of all these sums, dP plus PM here, and if P was here, imagine P was here, dP plus PM here again, which one is the shortest? Because you want the smallest possible value, right? And the answer is, you have to draw the straight line from D to M prime, right? And then the P will be cutting this line at some place. Let me do that. And that will give you the shortest possible distance, the shortest possible sum. So if I choose P to be here, if I choose P to be where the straight line from D to M prime, right? A straight line, where it cuts this line here. If I choose P to be that one, then what happens is that dP plus PM is smaller because it's a distance from D to M prime, be smaller than this. Right? Another way of looking at this is that the sum of two sides of a triangle is always larger than the third side. So this plus this will be larger than that. So where did this line here come from? It is simply by reflecting M to get to a new point M prime, and then joining that, and the P that we're looking for is this one here, right? So that P will give you the smallest possible value for dP plus PM. But now the question is, what is dP plus PM in this case? So the answer in this case is that when P is this point here, then that gives you the smallest possible sum, and it is dm prime. dP plus PM prime is dm prime because it's a straight line. So now what is dm prime? Right. This is for smallest. dm prime is actually the hypotenuse of a right angle triangle. This whole thing, hypotenuse of a right angle triangle, where we know, because we chose this point here, M prime, in such a way that these two are equal, this will still be 3. And now this is the hypotenuse of the triangle, right angle triangle, and by Pythagoras' theorem, you've got this triangle here, DAM prime is a right angle triangle. One of the sides is 6, the other side is 9, and DM prime that we're looking for is the hypotenuse of a right angle triangle whose sides are 6 and 9. So the answer to this problem is that the smallest dP plus PM, dP The answer is square root of 145. All right, so it's a rather challenging problem, but the trick is to reflect m to the other side so that when you work out dp plus pm, there, in that case, you can actually see what the smallest possible distance, dp to pm. If you're traveling from d to m prime, you wouldn't take a circuitous route. You'll go directly to that via the straight line, and that will be the shortest possible distance. So we go on to the next problem, which hopefully is not so demanding. And what does it say here? In a convex n-gon, that's a polygon on the n sides, n greater or equal to 3, what is the maximum number of exterior angles that can be obtuse? We have to try to understand what the question says. So let's take a polygon, n greater or equal to 3. Okay, so for a start, let n be equal to 3. So a polygon where n is the number of sides is equal to 3 is nothing else but a triangle. If you take n to be a four-sided figure, then an n-gon is a quadrilateral. So you've got various kinds of figures. For n equals 5, you'll have something like this maybe. All right. So this is n equals 3. N equals 3, n equals 4, n equals 5. These are just some examples. N, nothing is said about n. All we know is that n is greater or equal to 3. So you could have n equals 100. And then the diagram becomes very complicated. But the question is, what is the maximum number of exterior angles that can be obtuse? So let's look at the exterior angles of a triangle. And you will see that the exterior angles of a triangle, if I draw them out, I'm going to get one exterior angle, another exterior angle, another exterior angle. And you can see you've got all these angles are obtuse. But what do you mean by obtuse? An obtuse angle is an angle which lies between 90 degrees and 180 degrees. It's an angle which is bigger than 90, but less than 180. So such an angle is called an obtuse angle. A right angle is not an obtuse angle. It's called a right angle. And this angle here, when n equals 180, sorry, the angle A is 180, then it'll be a straight angle. Okay, so you can see here that all these angles are obtuse. If you try this one here, you will see that if you go from so let's just draw the exterior angle. So straight away you see that you got an acute angle. So this doesn't work. Now the question is it possible to draw a quadrilateral where all the angles are obtuse? Or likewise, is it possible to draw a pentagon where all the angles are obtuse? You want maximum number of exterior angles that can be obtuse. So can you have more than 3 angles which are obtuse? All right, so you see the exterior angles, one very important fact about an exterior angle is that if you draw the exterior angles of any quadrilateral, The way to draw an exterior angle is you start from one and you go extend it. You got an angle here. So you get an angle here. Okay, now from here, now you carry on, extend it, you get a new angle form. From here, you carry on, extend it, get a new angle form, and the same thing. So this gives you 4 exterior angles. And you can see I've got that are exterior, but this is not. So in this case, the number of exterior angles is 3, and here the number of exterior angles 3 again. And when you look at this, you will see that again the number of obtuse angles, which are exterior angles also, will be 3. So how do we know that? So one very important fact is that the sum of the angles, when you add these 3 angles, sum of exterior angles, very important fact for any polygon, is always the same number. It's always 360 degrees. So when you add these 3 angles, you're going to get 360. When you add these 4 angles, you're going to get 360. And likewise, if you add these 5 angles on the side, extend that, extend that, extend that, and so on. Keep going in the same direction. So you go, carry on, take a 10. So now you'll see you've got several angles here, and all of them, none of them seems to be obtuse. Maybe this looks like a right angle, but this is an acute angle. So here you have only one obtuse angle. Here you got 2 obtuse angles. Here you got 3. So the question is, what is the maximum number of exterior angles that are obtuse? So the answer is that if you've got n sides, if you're given n sides, so the n exterior angles, I'll put ext for exterior angles. Right? And let's give them names. We'll call it A1, A2, up to AN. And you want to know what is the largest number of numbers here which can be equal to, which are obtuse. So but we do know that when you add all these exterior angles, you're going to get exactly 360 degrees. So the question is, how many of these are greater than 90 degrees, right? So that's a problem. If you count the number of angles which are greater than 90 degrees, you can have 1, you could have 2, you could have 3, because 3 times 90 is 270. You can have 3 exterior angles. But the moment you come to 4, then they are all greater than 90 degrees. So when n is greater or equal to 4, the sum, sorry, the writing here is very bad. If n is greater or equal to 4, then at most 4 angles are obtuse, at most 3 angles. At most, because you can't have more than 3 angles which are obtuse, because then you have the sum equal to 4 times 90 is 360. So those 4 angles will be greater than 360. That's not possible, right? So you can have 3 angles obtuse, but not 4 or more. So the answer is that maximum number of obtuse angles is 3. That gives you the maximum number of obtuse angles. So that brings an end to this session, and we will meet again in session 8 when the time comes. Thank you for listening.